Welcome back. So in the previous segment, we looked at the Reynolds transport theorem, and you recall that we said back then that this was in preparation for our study of balance laws, right? Our continued study of balance laws. In that context, we saw how the mass balance law works out, and we saw a few other things. We understood the physical aspects of the Reynolds transport theorem, right? The physical interpretation, and so on. Now, we're going to forge ahead, and today, in preparation for our eventual derivation of the balance laws for linear and angular momentum, we're first going to study linear and angular momentum themselves, right? So that's going to be the bulk of this segment and perhaps the next two. Okay, so we are going to address today linear and angular momentum. All right. The way we'll start about this is to first, just to get ourselves on the same page, so to speak, we're going to look at how this works out for particles. Okay, so let's suppose we have a particle there. We label it by its mass m and its position vector. Okay, that position vector we are going to label as x, because we are really looking at this as the spatial placement of the particle. Okay. And let's go ahead now and write out the quantities of interest here, right? Let's suppose that this particle is moving. It has that velocity vector, right? That is its spatial velocity. We'll start out by writing its linear momentum, right? So the linear momentum we're going to denote it as L, and we're going to write it as a function of time. All right. The linear momentum now is defined as the mass times the velocity. All right. We have that for the linear momentum, and let's talk then about perhaps the most elementary of balance laws that you know in the context of the mechanics of particles, right? Which is the balance of linear momentum for this body, right? So remember what Newton's laws say, or what is often called Newton's first law. Right? Newton's first law addresses the rate of change of linear momentum, right? So in order to talk about Newton's first law, we first need to talk about the rate of change of linear momentum. Right? This quantity is, of course, L dot, and it's very easily defined here as m v dot. All right? And of course, we know that v dot, being the rate of change of velocity, is the acceleration, so we often write it as m a. Okay? All right. So, like I said, Newton's first law addresses the rate of change of linear momentum, and the statement of the law is that the rate of change of linear momentum is equal to the external force acting on the particle, right? So, so it addresses the rate of change of linear momentum, and let me say this. Let me just state this here. It says that rate of change of linear momentum, right, is equal to the external force. Right, and let's for now let's be using lowercase f as the force vector. Okay, so essentially what this says here therefore is that L dot equals, I'm going to write it in all its forms here because we will at various times use different ones of them. Okay, this is equal to F, right, and of course the force may be a function of time. Okay, so that's our balance law of linear momentum for a single particle. Okay, what we will do is go ahead now and also extend this to angular momentum. All right, okay, so angular momentum we're going to use a different symbol obviously for angular momentum, and I just realized that I need to make it clear that this quantity is a vector. All right, okay, L is a vector, right, the linear momentum. Okay, so the angular momentum. For the angular momentum, we are going to denote it as J, okay, it's a function of time, and this is defined as follows, right? It is essentially the position vector that I have already in this figure, and that is my position vector, right? That position vector crossed with the linear momentum. Okay, so it is x cross L, right, which of course is just x cross mv. Okay, now because of the fact that x is a position vector, what we have in this definition that I've just written is also the idea that we have defined here the angular momentum about the origin, and perhaps for the first time in the series of lectures I'm going to label the origin as the zero vector here, right? Okay, that's the zero position vector, or you can think of that as O, it doesn't matter. Okay, so we're going to denote this as J naught. It's also a vector. All right, so that is our angular momentum. Okay, now a few segments or maybe even a couple of units ago I mentioned that like our laws given to us by Newton that are related to linear momentum, Euler's laws are the ones that address angular momentum and its rate of change. Okay, so Euler's law here is right. Euler's law is that rate of change of angular momentum is equal to the external moment on the particle, right? All right, so let's write it out mathematically as well. So the rate of change of angular momentum, of course, is just J naught dot, okay? And that is d dt. I'm going to write it out again. I'm going to write it out again explicitly in all its possible forms. Okay. Now that written out formally is x dot cross L plus x cross L dot. All right. Now, on the previous slide, we have L and L dot, and those are easy enough to recall, so I'm going to just put them down here without having to look at the preceding slide. So L, you recall, was mv, right? Plus, so that is x cross m v dot. All right? But now we observe that what is x dot? X dot, after all, is just the velocity itself, right? And any vector crossed with itself gives us 0, right? So this term equals 0, right? And what we're left with then is that j naught dot is x cross mv dot, okay? And then invoking Newton's law for mv dot, which is the rate of change of angular momentum, right? Right? We see that the rate of, mv dot is the rate of change of linear momentum. I caught myself there. Making that substitution, what we see then is that the rate of change of angular momentum, which is j naught dot, is indeed x cross f, which is what we mean by the external moment. All right. So we've got to where we wanted with regard to our balance laws for linear and angular momentum for particles. All right? Okay. What we will do now is, in preparation for what lies ahead of us, which is that, of course, we want to go away from particles, right? We want to go to our continuous bodies, right? Where instead of the mass of a particle, right, we need to define, for this body, we've already defined the notion of the mass density, right? So we have mass distributed in this body, that gives us the mass density, and what we need to do is essentially write out these ideas of linear and angular momentum and their balances for this body with distributed mass. Okay? All right. So let's prepare for that, and okay. So now what we want to do is extend this idea extend the idea or extend the definition, the definitions of L and J naught to continuous bodies, or maybe just say continuum bodies. Okay? All right. So here is the picture. We have our basis, as always. We have the body in its reference configuration, omega naught. We know that here we have our mass density, right? It's a function of position only, and for position vector we have that, okay, and that is the position vector, right? And then of course we know that we are always interested in motions, right? Taking the body into its current configuration, right? Here we've defined the mass density per unit current volume, right? That's rho, which can now be a function of both the spatial position, let me say that is the spatial position, and a function of time, right? And do I risk trying to connect this up with a vector? Okay, let's try. Okay, so that vector continues across the body. Okay, there it is. Okay, so this is the situation we have. And in terms of our props, Just need to very quickly construct my basis here. Okay. All right. There we go. All right. So this is the setting. We have here our body in its reference configuration from the basis, from using the basis and from the origin, right, which is at the where the basis vectors meet. We have a position vector, right, to some point here. Then in the current configuration, we have the same thing going on, right? We have the body here, we have maybe it's deformed and all that, right? And we have the position vector there, right? So this is essentially what I've drawn out here. All right, let's write out our definitions of linear and angular momentum here. So the linear momentum, L, okay, it remains a function of time, okay? And this is defined as the integral over omega naught of rho 0 x, rho 0 is a function of x, times the velocity x comma t, right? Velocity is a function of reference position in time, integrated over the reference volume. Okay, and the idea here is that the product rho naught dV gives us an elemental mass, right? And so this is essentially every elemental mass distributed over the body in its reference configuration, multiplied by the velocity, integrated over the volume of the body in the reference configuration. Okay, and we know that that there is an equivalent description in the current configuration, and let's write that. Okay. Right, so the way we would write it out in terms of the current configuration is to write it out as an integral over omega t, right, over the spatial or current configuration of the body. And we know that this integral that we've written on the left here becomes rho function of spatial position and time. The velocity is the same physical velocity, but here we use the spatial representation of the velocity, and we have d little v. Okay, and once again, the product of rho and d little v gives us elemental masses, right? Multiplied by the spatial velocity, integrated over the body in the current configuration. Okay, so that's our linear momentum. Likewise, let's write out our angular momentum, and we will stick with the angular momentum defined about the origin. Okay, very much like we have up here, integral over omega naught. Now, reference position x crossed with everything that went in the previous integrand. All right. Okay, so what we're doing here is taking the cross product of every position vector x with now the linear momentum of every elemental mass whose product is given to us once again by rho naught and dV. Okay? And this now, so this is the angular momentum expressed with respect to the reference configuration, right? This is the angular momentum of the body in the reference configuration. Okay? Now, however, observe that the reference configuration is not the one that is of interest to us here, right? Because the reference configuration, really the way we're setting up our treatment of continuum mechanics is, it's really, because we're looking at the body occupying different configurations at different times, the reference configuration was sort of the initial angular momentum of the body, right? The reference configuration gives us the initial angular momentum, okay? However, what is really of interest to us is the current angular momentum, right? So rather than use this, we're going to do something different. Right? And because we're not going to use this particular quantity, and because I do want to make use of the same symbol J naught, I'm going to define this as a J naught bar. Okay? So this is not what we will use. Instead, right, so let me say that this is effectively the initial angular momentum. Okay. The current angular momentum, which is the one that we really want to use, is the one that will get exclusive use of the symbol J naught. Okay. and this is defined now over the current configuration because that is what is of interest to us at the present time. Okay? The current position crossed with the elemental linear momentum of a little particle, of a little amount of mass dm, right? And that is given to us by rho, function of x and time, spatial velocity, d little v. Okay, and to make it clear, I'm going to write here that this is the current angular momentum. Okay, and I observe that now I should correct what I wrote out here. Since it's the initial angular momentum, I have to get rid of this dependence upon time, right? The initial angular momentum was just for that initial time, okay? So I've got rid of that dependence upon time, okay? But the current angular momentum, of course, is one that will remain a function of time, so this definition is fine, okay? Actually, to complete it, we should also probably state that t goes to t0, all right, to indicate that all of that is initial. Okay, all right. So we won't revisit this initial angular momentum. It's really not of interest to us. We will work with the current angular momentum. And just to finish up this segment, let me introduce just two more quantities which will be of importance as we go ahead. And well, it's actually one quantity, but it can be written in two ways, which is the notion of the center of mass. Okay. Okay, and this idea is the following. So we have our basis, we have the origin, and supposing this is the body in its reference configuration, okay, that is some particle x, and we know about the density rho naught. Okay, we have here the notion of the center of mass, which is going to be defined here. I'm going to use the symbol uppercase G. Okay. And G is defined as the integral over omega naught of rho 0, function of position, times the reference position of every particle, integrated over the volume, divided by the total mass of the body. All right? So this is the center of mass in the reference configuration. Okay, so center of mass in omega naught. Okay, and really you should read that sentence as the center of mass of the body when the body occupies the configuration omega naught. When the body goes to a different configuration, omega sub t, right? It has density and it has a position little x, right? Here we have the center of mass defined similarly, but just via integrals over the current configuration, right? So rho multiplied by x d little v, okay, divided by the mass, which of course is the same, but still we are going to write this mass explicitly as an integral of the current density over the current volume. Okay, so this is the center of mass of the body when it occupies the configuration omega sub t. All right, in general, of course, G is not equal to little g. All right.